Now we come to one of the last topics in the course, the Iwahori Hecke algebra, also known just as the Hecke algebra, although Iwahori really invented it before Hecke did. And this originally was used in Lie theory and then became popular again, Lie theory in the 50s and 60s, and then became popular again in the 70s and 80s because of its connection to quantum groups. For us, we can look at it as something that's very closely related to the symmetric group that might help us understand representations and characters of the symmetric group a little bit better. I'm going to write HNQ for the Hecke algebra. There are really many Hecke algebras. This is the Hecke algebra of the symmetric group. Also called type A. So this is the non-commutative ring generated over Laurent polynomials in Q with integer coefficients. Sorry, Laurent polynomials in square root of Q with integer coefficients. By elements TS1 through TSn minus 1. So the indices here are generators of the symmetric group. And I'm going to write the identity element as T sub E, T sub the symmetric group identity element. Subject to relations that look a lot like the relations of the symmetric group. Now, generator squared is not equal to the identity, but it's equal to Q times the identity plus Q minus 1 times the generator itself. We have a braid relation, TSI, TSJ, TSI equals TSJ, TSI, TSJ, if I and J are exactly 1 apart, and TSI, TSJ equals TSJ, TSI. These generators commute if I and J are at least 2 apart. Now, if we have a reduced expression, let's say W equals SI1 through SIL. If we multiply the corresponding generators of the Hecke algebra, we're going to have lots and lots of indices. We'll have something like T sub S sub I sub 1 times T sub S sub I sub 2. So if that's a reduced expression for W, let's write TW for T sub S sub I sub 1, T sub SI2, etc. up to TSIL. Now, in fact, this product does not depend on the choice of a reduced expression for W, because of the relations, the braid relation and the commuting relation that look exactly like the symmetric group relations. The different reduced expressions are going to lead to the same product. This doesn't depend on the choice of a reduced expression for W. Another important fact is that if we plug in root q equals 1, well actually root q hasn't come into the picture yet. It will eventually. So I could be defining this as a ring with scalars z polynomials in q and 1 over q. 1 over q is not coming into it either, but that will come in very shortly. So if we substitute root q equals 1, or just q equals 1 if you like, then you can see that we get the symmetric group algebra back. So integer linear combinations of symmetric group elements. Because any generator squared is going to be, if q is 1, then this is 0. We just get generator squared equals the identity. So that means that every equation that holds in the Hecke algebra, if we specialize it at q equals 1, we get a valid equation in the symmetric group algebra. All right, now a couple things that we need to look at in Hecke algebra is how does multiplication work and how do inverses work. Every element TW is invertible. It's not equal to T sub W inverse, but it's invertible. So a formula for T sub SI inverse comes from this equation right here. And if that's invertible and T sub W is a product of them, then we'll just write the inverses in reverse order and we'll find an inverse for TW. All right, let's see if we can get an inverse out of this. If we put this term with the TSI in it on the left-hand side, then we'll basically have identity on the right-hand side. And then if we can factor a TSI out of what's on the left-hand side, then we'll find the inverse for TSI. So it's invertible because TSI squared minus Q minus 1 TSI equals Q times the identity. Which means that so if we divide both sides by Q, then we'll have identity by itself. And then if we factor a TSI out, let's say on the right, then we have TSI minus Q minus 1 TE here equal to the identity. So that means that this whole thing multiplying TSI to give us the identity must be the inverse of TSI. So that inverse is Q inverse TSI. We can say, oh, actually we have to multiply the Q inverse by this. So minus 1 minus Q inverse TE. And I guess we could make that a little bit nicer still. I'll keep that relation there. So we could say TSI inverse equals Q inverse TSI. It'll be minus 1 and plus Q inverse, plus Q inverse minus 1 TE. All right, so now that we see that TW inverse is not in general equal to T sub W inverse. And the reason is that T sub SI inverse is the same as T sub SI, but T sub SI, that element inverse, is not equal to TSI. It's equal to this expression here. As a corollary, we have that conjugation is a little trickier in the Hecke algebra than in the symmetric group. So T sub U V U inverse is not conjugate to TV, but TU TV TU inverse is conjugate to TV. Obviously, if we take something and left multiplied by another element and right multiplied by the inverse of that element, then we have a conjugate. But TUV U inverse, all in the subscript, does not have that form, even though it sort of looks like it should be conjugate to TV, but it's not. This is the right definition of conjugation. So inverting is a little more complicated. Conjugating is, it's not really more complicated. We just have to remember what the basic definition of conjugation is and not fall into the trap of thinking that this is conjugate to TV. Multiplication is a little more complicated also. Let's look at the product TS times TW. So this is equal to T sub SW if SW is greater than W in the Brouwer order. And it's equal to Q minus 1 TW plus Q T SW if SW is less than W in the Brouwer order. This proof is not too difficult. I will leave it for homework. And one thing that I guess is just as easy as in the symmetric group algebra, so if we're at ZSN, that's the integer span of W for W in the symmetric group. In the Hecke algebra, HNQ equals the Z root Q 1 over root Q span. Guess I should have that in the subscript. of TW for W in the symmetric group. So the dimension equals n factorial as a module over this ring with root q and 1 over root q in it. So that's it for the basics. The end.